Hi, everybody.
Hi.
Hello.
Hello.
Howard, you're muted. Howard, you're on mute.
Hi, Dan. Hello,
Hi,
everybody.
Tom.
Hi.
Hello.
Yeah, that's long hair.
Yeah, COVID haircut. I have one too.
That's right. Yeah. Where are you, Dan?
Oh, we're good out here in the country. Yeah. Hi, Don. I see you.
Hi, Dan.
Hi.
Uh-oh.
There's two tongs. Do you have a twin tong? I thought
It's
I.
fun.
Okay.
Oh,
That
no.
was fun.
Okay.
Now
Oh.
there's two. Now there's two Dons. That's funny.
No, there are?
Yeah.
Oh, let me get rid of one of these.
Hi, Howard.
What happened there? CLH is not me.
Okay. I think everything's more or less working okay.
Mhm.
Can everybody hear me okay?
Yeah.
Yes.
Good.
I can.
I'm going to go shut the doors because I think there's some noise coming from the other room. Hi, Rachel.
Okay, now I can hear. Can anybody hear me?
Yes.
Oh, good.
Yes.
So of course, the first evening of the workshop, my microphone said it wasn't working as soon as I logged on. Why wouldn't it? Of course. Okay, so it's 6 o'clock. It seems that we have a pretty good showing here so far. You know, some of you show that your microphone and your video is turned off, at least on my screen here. So for those of you who can hear my voice but don't see anything, check your video and audio settings on your own computer, and hopefully you'll be able to join in the fun. So we're going to start, and people can join as they are able to. I'm Howard Banich. I'm the chair of the Alt Ads workshop for the last, I don't know, maybe 5-6 years. You know, Russ Genet is our founder, and he'll have a few words for us after I'm finished speaking, which will be in a few very short minutes. I just want to say a few words about, you know, this year's online workshop and how this is our first time doing anything online, using any electronics. The most electronics intensive thing we've tried before was having a big screen TV to plug our laptops in to show our presentations on in Dan Gray's workshop. And sometimes we had problems with that. But hopefully today will go well, the next 3 nights as well, and we'll have minimal technical difficulties as we hear some, what I think will be some very interesting and thought-provoking presentations from our speakers. So also a few words that I've learned about Zoom is if you can wear a headset or earbuds, that'll cut down on feedback, and you'll all be able to hear the speaker much better. And really, that's about it. I know a few people freaked out when this didn't start at 5 o'clock, but we were scheduled to start at 6 tonight. So hopefully those people are now logged into our session right now. So without any further ado, because I'm not a very good extemporaneous speaker, and we have Russ Genet, who is actually quite polished as such. He's going to give a few words about his perspective on the AltAs workshop and how we have come to be where we are. This is our 13th annual workshop, by the way. So I thought that was rather appropriate for 2020 and everything else that's gone on. Have our 13th annual. So Russ will say a few words. And so Russ, if you're out there, I think you are.
I am indeed.
There you go. Take it away. Thank you.
Okay, they'll do the share screen. Host is disabled, participant screen sharing.
So let's see here. All right, try now.
Okay. There we go. And we'll do a share. And we'll get rid of this. Let's just minimize that. And get the full screen here. Okay, is that showing up as full screen?
Yes, it is.
Okay. So, yeah, I decided, let me start timer here. This is my approach timer I use for instrument flying. At any rate, so there's a number of people that haven't seen kind of the early slides and stuff. So I've got, I think, about just a dozen slides here, and want to mainly talk about the early days and how the AltAs initiative came to be. And, we're actually two initial meetings. And so we had one here at Cal Poly, and just some notes. So there are quite a few people have stayed with us. You can see Moon there, and there's Dan in the back, and there's Dave Rowe. Well, there's Tom Johnson, and at any rate, it was a nice meeting, and so that's when Dave and Dan first met. A number of us first met, and then we had a meeting. So this was the first one up at the TMS in Portland, and there's the and all 1, 2, 3, 4, 5 of us have stayed with it, and so that there's Dan's Lollipop, which was a really cool deal. I really like Lollipop. At any rate, and then the thing that impressed me most was, so when got to Portland and was waiting for the meeting to start, this van rolls up, the door comes up, and out rolls the pieces for Howard's 28-inch, and in minutes he had it assembled. I mean, I was just blown away. And Howard, so that, how many years had you had the 28-inch by that first AltAs workshop?
Well, the scope is 16 years old in total, and it was just a couple of years old at that time of the first meeting. Yeah.
Yeah, and I think it's it's always been, in not every meeting, but every few meetings there would be an upgrade on the 28-inch. I remember one time had the 28-inch, and we were thinking, okay, now if it had a 1 meter telescope and had a Naismith focus. At any rate, those were fun meetings, and while most of the meetings were at Portland, we also had quite a few other AltAs meetings. So in the upper left is a meeting we had in Hawaii, and I'm just looking to see some. So there's Richard, you're over there. That looks like Arnie Hendon standing. David Davis back there. And Dan, there you are over there. And Tom Johnson came to that one, Bob Buckheim and Tom Smith. Anyway, kind of the regular gang. And this picture over here on the far right, Richard, you took that picture, or you gave your camera to one of the assistants there to go up on around and take that picture. That was your wide angle camera?
That was a wide angle lens and it's multiple exposures. And no, they wouldn't let me climb up there, but he was willing to take the camera and shoot like 10 pictures. And I assembled them into a super wide angle.
Yeah, that's I love that picture. That's cool. So there's Altaz Initiative folks down there with our HADAs. So this is the 8-meter telescope up on Mauna Kea. So some other ones. So this is another different Hawaii con. This was over on Oahu, near where I stay. Cheryl and I stay for the past 14 winters. We're gonna miss it this winter. But this was over on the Big Island at Canada, France, Hawaii Telescope, and Howard. I know you were there, and
Oh, yeah. Dan was
yeah.
there.
Yeah, and Bruce Holenstein was helped organize it. At any rate, there was quite a few. That was a really good meeting.
Yeah, Bill was
This
there.
one here on the middle left was back at San Luis Obispo. We held it at the one of the only major hotels in San Luis Obispo. That was well attended, and this one here was up in New Mexico, up overlooking the White Sands at that big resort up there. And it was the 17th anniversary, almost to the day of the first remote access astronomy to the Fairborn Observatory 17 years earlier. And this one lower left was in Dallas, Texas. One thing had happened there. So this was where you can see Rick Hedrick here, Plane Wave, and I met Kevin. Kevin's in here someplace, Kevin Iott, and hired him. At any rate, there's, and this was Canada up at British Columbia, the University of British Columbia. Anyway, we had lots of that meeting, so there was lots of interchange, and then I think it's at the we gave it its name early on because this idea of there are things that big telescopes were doing that we could bring the technology to small telescopes. The big telescope folks were doing one-off, designs. They have big staffs, and they would design these telescopes and build them for many, many millions of dollars. And we thought, well, we could take their best features and turn them into something that's affordable and smaller. And so some highlights. So this telescope here is in New Mexico. It's up on Magdalena Ridge, and the mirror, the primary mirror that you can kind of see through the slit here, it's the spare Hubble mirror. It's the good one. They sent the bad one into space, and this is the good one. They put it on air cushions, but the key thing was, so Tom Smith and I visited that, and we spent the day. They actually took covers off. We crawled inside, but the key thing was it was direct drive, and that was very important. Here, Dave and I visited the outfit in Tucson that was making telescopes. Another Tucson visit, middle left here, Lisa and I went to the Mirror Lab and met with the folks there. She was very interested, in what they were doing there. Here, Dave Rowe and I, this is Roger Angel on the left, and we asked him about thin meniscus mirrors. He says, "Oh no, you don't want to do that." And then he went and did it himself a few years later. And most of the rest of these pictures are up on Mauna Kea. So we went up. Dan came over, and we had a really good time. We spent a week or so in Hawaii, And it was winter, so it was snow up on the Mauna Kea. That's the 8 meter. There's the let me move this out of the way, if I can. Yeah, there we go. So this is their cable wrap. This is the azimuth cable wrap. So this is all the cables and coolant lines. This is at the Subaru here. Dan had this was their control system engineer on the Gemini, and Dan and him talking buses and so forth. Here we met with the observatory directors. So this was the Subaru director and chief engineer. This is Doug Simons, who's been a friend of mine for a long time. He was the Gemini director, and he's now the Canada France Hawaii director. And there's, of course, Dan. And at any rate, you get the idea. Oh, here we're looking at a Renishaw encoder tape. It's not an 8-inch diameter, it's 10-meter diameter tape. They have really high resolution. Okay, so let's see if we can move to the next slide. Okay, and we produced early on a couple of books. The Altaz Initiative is a great book. So it was fairly thick, had lots of chapters by various things and on mirrors and all that sort of thing. And in 2009, 2010, we did a paper for the National Academy of Sciences and the Astrophysical Decadal Survey. I look back at it, it was pretty prophetic. We had already made lots of progress by then, and there's lots of there's Dave and Dan and Andy and Mel and Howard and so forth. At any rate, it was a great paper. And of course, there's always been, besides, how do we bring the mirror technology down? So there's been a little bit of large telescope. How do we make small telescopes have large mirrors? And yeah, Andrew and his glass foam, and I guess we're going to hear from Lisa with spin cast mirrors, and David Davis with his oven and slump mirrors, and then I think we're going to hear from Mel Bartels and rather successful meniscus mirrors, and then besides primary mirrors, we thought about active secondary mirrors and active shaping of primary mirrors even, and so there's and Bruce did stuff. Greg Jones had a cool project. And now at the that's an infrared telescope facility, but this was an adjustable primary warping system for his 8-inch telescope. That it worked amazingly well. You could take his mirrors that were definitely had all some adjustments and shape up the mirror. And but a key thing that this kind of went on for the whole Altaz initiative, besides our Altaz telescopes, was the direct drives. And so this was one of the Friday nights, the upper left here, at the Altaz initiative, and an early one. And this Dave Rowe had built this plywood direct drive motor, and this was the Friday night. The Dan's burnt chicken and Dan's generous cold beer. And anyway, then that led to the Cal Poly 18. Here's some of the students at Cal Poly that built it. They didn't do it quite right, so then Dan inherited it and worked on it. He and Howard and others for 3 years up at TMS, and then it went over to Richard Berry, and Richard worked on it a few years more, and recently it got moved back to Dan, so Dan's going to give it a home. But at any rate, but the Cal Poly 18, during the design review, before anything had been built, Rick Hedrick and Dave Rowe and Joe Haberman, the Planewave chief optical guy, they came up to the design review. And then the next morning, we all went for a brunch at the apple farm. And I asked Rick, I said, "So do you think you could build this commercially?" And so he pulls out the proverbial paper napkin, and we started estimating cost. He decided, well, we'll make it a 0.7 meter, and at any rate, to make a long story short, Dave spent the next couple of years with a crew, kind of honchoing the engineering to make the CDK 700 come up. So that's on the left there. And then we thought, well, it'd really be nice. The sweet spot is the 1 meter. So Dave spent 2 or 3 more years. And so we got the CDK 1000 now. And then the thought is begin to a 2 meter. And then the last, so this is the last slide, is Dan has been our, Dan, are you on?
Yeah, I just had to unmute. Can you hear me?
Okay,
Yeah.
yeah. Walk us through a few of these. So, so that's what I've got. But Dan, tell us about spreading the gospel to of direct drive and so forth to older telescopes around the planet.
I don't see any direct drive telescopes on this. So, oh yeah, this one here. Can you see my mouse?
No.
Okay. That's a 1 meter. You can see Hannah in the background. This one's in South Africa.
Oh,
So
yeah. So can you see my
yeah.
mouse?
Yeah.
Okay.
Yeah. Okay. So that's one that we installed, and we had all kinds of problems with the former software. So they finally switched over to our software, and it just discovered a planet, an exoplanet. I just heard about that 2 days ago, so that's pretty cool.
Tell us about some of the other systems.
Yeah. Okay. I'm going to start at the top left. So that's
Okay.
me, and that's a 41-inch English mount. What is that called in German? No, an English
yoke.
Thank you. English yoke mount. That's at Yerkes Observatory. And we ended up putting on some brushless motors on that. We didn't need encoders. They just use open loop. The one at the right there, I'm standing there working on a 24-inch, I believe, at Goldendale Observatory. And that's in southern Washington. So it's only about a 3-hour drive from our house. You can kind of see the Servo 2 on the open door. And that's a conventional just brushed DC motors. At the top right, I don't know what that is.
CTIO.
Oh, okay. So that's at CTIO. So go just below there, and that's a 1 meter Bowler and Chevins. And there's, oh gosh, I got to think of all their names now. Josh is on the left. He does the dome controls, and that's me right there. And that's Bob. He's a chief scientist on this project, and that's Tyler on the right. And we spent about a week there getting everything all working. That thing has just been a wonderful production telescope. They use it every night, all remotely. Nobody ever even goes in the building. And it does asteroid discovery follow-up. And Tyler kind of does most of that. He's a postdoc at least. Let's see. On the starting at the top left, just below that picture of me, you'll see those split rings there, right? And those split rings are so you could put an encoder around a telescope. So imagine you put those together on top of each other. You put it in a lathe that's just to the right of that, and then you machine it and you dowel pin it before you take it all apart. And then you wrap it around the axis, and then you put it all back together, and then you spend about 4 hours dialing it in with a dial indicator, moving the telescope back and forth, and you put the encoder tape on it, and now you have absolute encoders on. I don't see a picture of that telescope. Yeah, so that's at that one went on North Carolina at the 3 College Observatory, and I see that Marty is here tonight, and Marty is in charge of a telescope for well, his mic is probably muted, but anyway, it's in southeast Washington. It's by Walla Walla, and it's a sister telescope to that telescope, and we're doing the same modification on that very soon. Now that one interests me a lot. It's pretty cool. It's the third one. Yeah, that's it right there. That's an alt-out telescope for the University of Chicago, and they couldn't, I mean, they just gave us the contract, no bidding or anything, because nobody else could do an alt-out software. And it's a spectroscope. The secondary mirror moves by a gear half the speed of the telescope. So it always puts the light through that primary axis. You can kind of see the spectroscope on the right. The two at the bottom left are an RCOS at New Mexico Skies. That mess there is the wiring for the Force One controller, and then that's the telescope just to the right of it. And he got like a 3 arc-second RMS. He put absolute encoders on it. Lots of stories about that. I could go on and on. And then just to the right of that is, you know, people that are on the user group know Don Westergen real well. And Bob Harwell was kind of, we got this all put on the Force One and brushless motors on this German equatorial. I think it's a 24 or 28 or something. Let's see. And then just to the bottom right is a 36-inch telescope, Buller and Shivens at New Mexico Skies. It's the Middleman scope, and sadly, Middleman passed away from brain cancer just before this installation was completed anyway. So, but he's the one that funded it, and after he died and passed away, they wanted to keep going with the project. So that's there.
Well, thanks, Dave. I'll stop sharing and
Okay. So is that it for you then, Russ?
that's it.
Okay. Well, thank you very much. I always enjoy, you know, looking back at how we got to where we are and all the offshoots and everything that has been sparked in the projects that have come from it. So, yeah, and it's perfect that you let Dan talk for the last few minutes, because he's the next speaker. And now that his voice is all warmed up, Dan Gray, you're up.
Okay, well, I'm just going to share my screen. Let's see if that works. Oh, somebody told me to do this little option, optimize screen for, we have a couple of videos.
Yes.
Okay, so F5. Whoops, back up. All right, so this talk is about building a 36-inch, it's an F4, and it's portable, and I put that in quotes, Altaz with direct drive motors. And it went through a lot of design thought, and I finally decided to propose a direct drive system, and you'll see why in a few slides. So we're building it for Jimmy Lowry. Is that how you pronounce his name?
Lowry.
Lowry. Okay, he's a close friend of Howard's, and he's an incredible observer.
Oh, yeah.
He uses high power. He won't touch a paracore because he uses high power, and the glass of the paracore might eat up a few photons and they don't go to his retina. That's kind of his philosophy. Mostly galaxies, I think. I'm going to show you a slide next of his setup, and it's near the McDonald Observatory, right, Howard?
Yeah, West Texas.
And, yeah, and it's called Barbarella.
Yeah.
And I'm not sure where that came from.
Well,
Do you know?
I can tell you why. Yeah. The telescope was designed and made by the OMI company. I don't know what, 10, 15 years ago, whenever it was. And when they first put it together, they found out that their weight calculations were off, and the telescope was bottom heavy. So they had to put about 50 pounds of barbell weights up on the cage to balance it. And so the barbell weights, Barbarella.
Ah.
Yeah, he has
Now I know.
he's got a poster of the movie Barbarella on the wall in his observatory.
Oh, okay. I get it now. Thanks, Howard.
Yeah, there you go.
So
And there
here-
it is.
There's barbells up at the top right.
Yeah, there you see it. Yeah.
Well, that's a better problem to have than the other way.
Yes.
Yeah. So I guess he's not afraid of heights, huh?
No. Well, you know what? Because he's got great skies there in West Texas, being so close to the McDonald. But when you're out there, it's a 14-foot tall ladder, and it's dark. And once you start getting up the ladder, you can't see the floor of the observatory very well. So you kind of lose track of how high it is. Plus, you just want to look in the eyepiece.
Yeah. So
48-inch telescope, holy cow.
yeah. So Howard has flown down there several times just for observing sessions.
Oh, yeah.
Yeah. So that must be a real treat.
It is.
And can you tell us a little bit, Howard, about how Jimmy observes?
Well, in a few words, he goes all out. He is about seeing things that no one else has seen visually. He's all about trying to see things that, basically would strain your belief if you hadn't actually looked through his telescope and seen some of them yourself. He wants to basically push the limits for visual observing with today's technology. And that's why he doesn't want to have he doesn't need a paracore, because he never observes at a low enough power to benefit from one. Plus, like you said, why put more glass in the light path?
Okay.
Yeah, and that's about it. He's just a hardcore, all-out visual observer.
All right. So the only problem is he's mainly used the northern skies, and now he wants to take it to the southern skies. And Barbarella won't go on the plane with him, not surprisingly. And so his idea was to ship a telescope down there, put it in a trailer, and then he can fly down there and view the southern skies. I hope to meet him there sometime. So now we're going to talk about a little history. Oh, not yet. So this is Jimmy was communicating with Tom Osipowski about building it, and Tom wasn't excited about it. It was like too big and too, he's kind of, he's got enough business, and I don't know, he just didn't want to do it. So Howard, who's a good friend of Jimmy's, put us in touch. And so we started talking about this a few months ago. So now we're going to go to the history. And I think it was 1999, maybe 2000. I built a 28-inch visual string scope. And here it is in its first iteration. You can see it has a secondary that's folded back. That's called a folded Newtonian. It's got that cute baffle up at the top that looks like a Star Trek emblem. You can see at the bottom, you can see my mouse. This is an altitude clutch. You can use it in the drag and track mode. There's also an azimuth clutch. This has all been changed since then. Anyway, soon afterward, Howard improved on my design, and he built this telescope. And you can see he had two clutches. You can see the encoder on top of that. You can see the altitude clutch over here on the left. If you can see, can you guys see my mouse?
Yeah.
Okay, good. And this is an early Altaz workshop up at our shop at Technical Marine Service. Anyway, Howard scope is outstanding in its field. and this is an incredible view, don't you think? And not only that, but I think that the telescope is pretty nice too. And Howard has continually improved this telescope over the years. He second most recently completely redid all the drives and clutches, And thirdly, and the last thing he did was a high-tech ventilation system. I think we're going to hear about that later on. And then Tom Osipowski also improved on it. And there's Tom with I think a 24-inch telescope. Well, in 2000, oh, I'd like to tell about the phone call I got from Russ Genet. And this was in the early 2000s, and he was wondering about the our servo controller for telescopes. And I'd never met him. However, I knew about him because I had that book that he and, oh, I can't think of his name right now.
Mark Trueblood.
Thank you, Russ. Mark Trueblood wrote. And, you know, those, the formulas in there still work even today. And I used them on some of my software that I was writing way back then. And then I ended up going to that Cal Poly workshop that Russ had pointed out, and I met Dave Rowe. And what a great change in life, really a life-changing experience, to be perfectly honest. And out of that came the Cal Poly telescope, which Russ mentioned. So after the Cal Poly students graduated and went their separate ways, we took it up at TMS to try to make it work. And I don't know how many pounds of epoxy is on that thing to get the bearing straight and replace, you know, 2 bearings on each side instead of 1, and make one axis point to the other axis. And I mean, fork, it was it was a mess, really. But we ended up getting it working. And so then Richard and me basically tested it at our shop at TMS quite a few nights until we felt it was okay to bring it to Richard's place. And so he built a little shelter for it, and he was testing it and having some pretty good results. And then the encoder tape broke and peeled off, and it was a disaster, and it sat around for a while, but we did fix it. And then Richard went other directions. He had other things. And so he wanted to see what I would think about doing with it. Well, I have a place to put it. I have a roll-off roof observatory that it barely fits in. And I was wondering, have you guys heard of a takeoff roof observatory? There's a takeoff roof observatory. And there it is. There's a direct drive motor at the bottom. There's the other direct drive motor. I guess it's on that fork on the left. There's the encoder that's behind that wooden cover. I think Richard actually made that. And then it's got a focuser and rotator. And this is the model, one of the models that I made while we were testing it, while I was testing it. And this is the software that Dave Rowe wrote. And he and PlaneWave are kind enough to share it with all the SciTechers out there. And this one is a 3.7 arc second RMS with 4 points turned off, you can see. And then the following image is an image of NGC 891. And it's got 3 10-minute open loop unguided exposures stacked together. And I find that incredible. And it's because of the technology of direct drives and also Dave Rowe's pointing model, Point XP. So thank you, Dave. All right, so now we're going to get back to eVscope. And so I was thinking about making a mount similar to Howard's and Tom's. And then, you know, we've come a long way in making motors and, you know, that sort of thing. And so I started considering doing a direct drive. And so this is what I came up with as a preliminary design. And I think that the secondary mirror needs a little more support. And so does the focuser. It's just incomplete, really. And I will get some more details real soon. So the reasons is, you know, Jimmy uses high power, and it must be frustrating to go somewhere and it's not quite there, and you know you have to sync. He'll make a 16 point. That's going to be perfectly enough visual model at the beginning of the night, And then if he doesn't move the scope, you can use it any other night. And he'll have perfect tracking and centering. And so why not, even if it's a visual telescope? So I tried to think of reasons not to do it. And one, it's a heavier mount. And Jimmy didn't like that. He thought it was too heavy. And I kind of came back a week or two later and said, I'm worried if I make it lighter, you know, a direct drive mount has to be stiff. And so he became okay with that. So it requires a bigger battery and it's slightly more expensive. But when you're talking about a 36-inch telescope, I mean, the mirror costs, you know, a lot. And, you know, all the rest of the structure isn't going to change that much. The electronics are going to be a little more expensive. The motor is going to be a little more expensive because we have to build it from scratch. But in the large scheme of things, the slightly more expensive isn't a big deal. And a bigger battery isn't that big of a deal. So, you know, there's a lot of advantages to having a direct drive telescope. Probably the main one is accuracy. And then others are wind resistance and speed of slew if if you care about that too much with a scope that big. Okay, so I based my design on what is called a slewing bearing. And I'd never even heard this term, but I started looking at try to find a big azimuth bearing because you kind of need one. And I found a place, jcbbearing.com. And here's some pictures I got off their website. I didn't get permission to do this because I didn't have time. So I hope I don't get in trouble. But I'm sure it's just, you know, more advertising for them. So these are some slewing bearings. And basically, they're 4 contact point bearings. And instead of, you know, the balls are kind of in the gap there. I'll show you more of it. So one shortcoming of the slewing bearing is significant friction, and it's related to weight. And there's going to be about 1,000 pounds on the slewing bearing. And so I did some calculations with data that they sent me. Excuse me. And they're going to have about 20 Newton meters of friction component, a frictional component with all the weight on there. And so I was a little worried about that. And I think I solved that problem, as you'll see in a little bit. So we're going to build the direct drive motors. And we know how to do it now. And I'll show you. Okay, so we made a siderostat for the University of Arizona. And the big hollows that you see there is the light path of this telescope. And it hits 2 flats, elliptical flats that David Davis made. And it puts it down into the room where they're doing spectroscopy and stuff. So that's what this is about. This is Daniel, he works here. And this is our coil winding machine. So we use an airplane simulator, a flight simulator, pedals, and he's controlling the speed of the motor, the winding motor. You can see that thing is winding, and there it is, see? So every time it makes one revolution, that other one turns just the right amount. And we went through a lot of iterations of how to make coils, and this really works nicely. And you have to make sure that epoxy gets in all the windings. And we tried vacuum chambers, and nothing really had success until we did it like this. And this really works, and it's so cool. So I'm gonna, for the sake of time, I'm gonna advance this a little bit. And this is the software that's controlling it. And there's a configuration tab I won't show you, but it's counting the turns of each layer and telling when to go to the next layer and moving that little fishing reel setup. And I think we're done with this video. Okay, so at this point, I'm going to take a break from my presentation. There's a few more pages, but I want to show you some of the design that I've done for this telescope. And if anybody wants to interrupt me, just turn on your mic and interrupt me and tell me if you see a problem or if you see a place where I could improve. And I've got a piece of paper and a pencil down here, and I will jot down your suggestions. So here we go, interactive mode. Let's see, I want to find this one first. So this is a mirror cell. And you can see that the mirror hasn't been silvered yet. And I'm going to turn the mirror off so we can see more details. And I'm going to turn the whole shoot and match off and zoom into this little part right here. Okay, so this outside part is going to be like a piece of plastic tubing, or we might 3D print something. And then the inside part is a 632 threaded rod, probably, or screw. Okay, I'll turn that back on. I'm going to just turn on okay, so this is one of the wiffle trees without the bearings on them. And I put a lot of thought into this. And it has 2 pieces of steel, 1/8 inch steel, I think. And I'll turn that off. And then it has 3 pieces of aluminum that are you know, CNC'd. And that right there is a bearing. There's 2 bearings. And then this is a 5/8 post that's welded to the cell frame. And then there's a little spacer right here to keep it up. And then there will be a threaded, like a nylock or something at the top. So that's the wiffle trees for the edge support. Okay, so let's turn these guys off. And we'll go back to, I guess we'll turn on the whole mirror cell and start looking at it. Oh, I need to break out of here real quick and show you a couple of pictures. Okay, so this is a picture of a spherical bearing that I got from McMaster Carr, thinking I would be using that on the cell plates. 30 seconds after I got it in the mail, I realized it wouldn't work. As soon as you put weight on that, in that direction, there was so much friction, there's no way it would have ever worked. And so then I started experimenting around. I got a brass acorn nut, and what you see here is, you can't see it, but there's a hole drilled in this piece of steel, and there's a chamfer on it. So it's just a regular angle chamfer. And I can put as much pressure I want on that screw, and it still turns, or, you know, easily. So I'm sold on this. The problem is that an acorn nut isn't going to work because there's really nothing in there, and I need to tap a hole in it. So we have a CNC machine lathe, and so we're going to make them on that. Okay, so now we're back to the show here, or the interactive. So I'm going to turn on the small spheres and big spheres, and we're going to zoom in. What's that doing on? Okay. So I'll start looking at the big spheres first. And whoops. So here's a sphere, and then between this and this is a plate. And I think if I put on the, yeah, see, now you can see the flathead screw that's just keeping it. There's no tension on it. That screw bottoms out in the threads, and you can see underneath it, it rides on that. But that flathead screw keeps it from falling out under. And then here's the other smaller ones. If you turn on the other parts, they sit there with another. These are 632s. That's a 1032, I think, on the big plates. So now I'm going to turn these all off, and we'll go back to the design. Now, what you notice on these 3 plates, the 3
Hey,
big
Dan,
plates.
Rob
Yeah.
Brown here. I didn't understand why you couldn't use an acorn nut. It seemed perfectly fine.
Well, because I needed to tap a hole in the end of it. And the acorn nuts that I tested, it's all hollow up there. They solder a little shell on top of it, so it wouldn't work. That's why.
Oh, I thought those were solid brass. They're
I
not.
did.
My
I did
God.
too. I mean, maybe
Ah.
there are some, but this way I can make them exactly the way I want them anyway, because it'd be hard to find that. But thank you for that question. And the other thing that I'm going to do is I'm going to make them out of oilite, and probably many of you know what that is. It's a bronze alloy that's impregnated with oil, I think, or graphite or something, and it's self-lubricating. So that'll be a big help too. We'll probably 3D print these little mirror contact points. And remember that part that I showed you that had the little plastic piece that slipped over a 632 thread? Well, see where my mouse is. One goes in there, one goes in there. That keeps this thing from tipping back and forth. One goes here and here. That keeps this plate from going or, turning. And then one here that keeps this plate from turning. And then there's 2 that are pointing down that go by the cell frame, which keeps the main plate from turning. And they're all like, all 3 are like that. So just those holes in the main plate keep everything steady. So that's one thing I thought about quite a bit. And then these are the mirror keepers right here. And you notice that this was on the side of this bracket here because of space requirements. And so that means if I turn on the mirror, you'll see the covers, but these are all 120 degrees apart. And that's why this one here is longer than this one here. And so that's the mirror keepers here. Now, there's also mirror adjusters. So if you look in the end of this, now this one was the first one I did, like this was my 28-inch telescope in the early 2000s. So this part right here is a piece of plastic, and it's got a threaded hole in the middle, and it's made to fit tightly inside this square stock. And on the bottom, there will be either a jam nut or what do you call those? It slips my mind right now. The kind that don't turn unless you really refine a nylock nut on the back. That's how I do my 28, and that's always worked really well on my 28-inch. And so I stuck with that part of the design. These are bearings. They're 1.25" bearings, I believe. And we're going to 3D print a piece of plastic that goes around them, some kind of material that Taj, he knows everything about 3D printers. He'll recommend what kind. It's got to be hard because we don't want it to compress. So whatever he says we'll use, we'll probably 3D that so it won't be metal on glass. So before we leave the mirror cell section, does anybody have any comments or suggestions or questions?
Well, you answered all my questions in the course of your description.
Okay.
The one last thing I would ask is, are you planning on painting the cell or powder coating or what?
Yeah, we'll probably powder coat it because it's all steel.
Mm-hmm.
Yeah, I mean, I know that's what we'll do. Okay. So now we're going to switch to this is a slewing bearing. I showed you a picture from the factory. Now you see this dimension here. It's really meant to be this way. This is how it came as a drawing. And you can see that the outer ring is higher than the inner ring. And this dimension is about 32 inches. It's just under that dimension. That's how big this slewing bearing is. But we're going to use it this way, like that, because I want the outside part to be the most stable part that is, connected to the ground via the ground structure.
Dan, how much does one of the bearings cost?
Okay, so this one cost about $1,800 plus shipping. So This is a major part of the cost. Well, it's about the same as one of the encoders. Encoder is a little more, but it also weighs a lot. It weighs 275 pounds. But fortunately, it's at the very bottom, so that's good. All right, so let's turn off some stuff here so you can see what it looks like on the inside. So there's bearing balls. I'll turn the balls off, and the groove. This is just a spherical groove, but the groove is shaped a little funny, so there's only 4 contact points. So that's the slewing bearing. I think we're done with that pretty much. Now we're going to see the motor. Now this motor, I've spent a lot of time designing this thing. This is a slewing part right here. Turning it off and on. And I'm going to turn it off so we can just try to imagine it. So it's upside down from where the factory had it, but they said it was okay to use it either way. This part right here connects. This part here turns. The part that's yellow turns, right? This part here connects the magnets to the part that turns. This part right here, okay? So now I'm going to turn this off so we can see the insides. Underneath is a piece of aluminum. It's 3/8 thick, and I was worried about, Dave Rowe says he gets paid to worry, and I really understand that, I didn't want any vibrations from the magnetism and the PWM of the magnetism and resonant frequency. So this is a 3/8 piece of aluminum. On top of that is a 1/8 piece of steel. And these are the coils right here. I'm going to just turn off some of this other stuff so you can see it. Okay, so this is a set of coils, and they're screwed onto the plate, right? So on top of that are the magnets. And remember, I was mentioning that, there's some friction component to this slewing bearing. Well, that's why I'm using a double motor on the azimuth. And so there's coils on the bottom, and there's coils on the top too. See that? And if I zoom in on this, you'll see a nice gap right there. Turn on the coil top plate, and the top plate connects the top coils, which are stationary. They're stationary. So this whole bottom part is stationary, and it holds this top plate right here, which is 3/16 steel, to these coils. So this motor is going to have twice the torque for a given current. And that will save on batteries, and it will save on we'll be able to use lower voltage, and it solves a lot of problems. Okay, so now I think everything is turned on. Let's see, most things are turned on. Okay, so now this is how we connect the rotor. I'll turn back on the slewing bearing. There we are. Okay, so one last thing to look at is this is the encoder bracket, and we designed these for the Atlas project. We made 2 mounts for the Atlas project, which you might have heard of. And if I turn this off, so we're going to water jet this plate. This is a 3/16 plate. I'll turn it back on. So this dovetails into there. And actually, Russ knows all about this, don't you, Russ?
Yeah, they work great. It's wonderful.
Yeah, so there's a spring between here and here. This is threaded right here. And then you can just turn that screw until you get a blue light on your encoder. And then you tighten these 2 set screws that lock it into the dove. And then this mechanism here is the only way I could think of to connect the ring, the encoder ring right here. This is the encoder ring to the rotor, because that has to turn. So these 3 things, I didn't draw the bolts in here, but that holds this steel plate right here, and that's bolted to the steel plate, and this is bolted to the ring. Any wires that come up can go through this center part. And so this is what I came up with. Now, I think I'm done with the motor. I should go back to it and ask if anybody has any questions or comments or suggestions.
Question, Dan, can you hear me?
Yeah, loud and clear.
Oh, great. So on the slewing bearings, are you okay with them without having a spacer or a carrier between them?
I guess I don't understand your question. A spacer or carrier between what?
Between the slewing bearings, the individual bearings.
Well,
Normally you would see in a configuration like a spacer so that the bearings don't touch each other because they're rotating.
oh, yeah,
the
they
ball
don't.
bearings.
Yeah.
Yeah.
Let me see if I can call up a PDF real quick. So this
Yeah,
is
normally they wouldn't touch it. Yeah.
so this is their drawing, and no, they don't touch each other. They only touch their balls, and then okay. And then there's a seal on the top and a seal on the bottom to keep out dust. So this is their drawing.
Right, but the bearings don't touch each other side to side. They're separated.
Oh, I see what you're saying. Like a cage, a bearing cage.
Yeah, bearing cage normally we would see to
Yeah.
keep them separated. Yeah.
Yeah, I think that I don't really know the answer to that question. All I know is that they gave me the frictional component, and that's why I made the double motor. So we'll have to see. Maybe they do cage them. I don't know. Anyway, that was a good question. Anybody else?
Just a thought, Dan. The structure you made to center the encoder ring, with the 3 arms and the circular cutout in the center, and then the encoder on the bottom. Couldn't you just do away with that? If you're gonna water jet out the top ring, why not just have the design arms coming from the inside edge of that ring to hold the encoder?
So make that ring longer. Well, one of the reasons it's higher.
Oh, it's higher. There you go.
Let's see.
Okay.
And let's see if
question.
It could work. Well, it has to be above this plate because that plate right there is stationary, right?
Right.
And so the encoder. That's an interesting idea. I'll spend some time thinking about it. So I would have to lower the ring a lot, and then this is going to hit the ring, so I'd have to lower that to underneath. That's an interesting suggestion, and I never really approached it that way. And maybe I can do that because that would just be a bigger piece, or a different water jet cut.
Yeah, or maybe the encoder just sits on top of those arms instead of having to lower it down.
Yeah, that's what I'll look at that tomorrow and see if that's going to see if that could work.
It could.
Yeah.
Anyway, just thought.
Yeah, it's a good thought.
I'm going to ask a question that shows I really don't know what I'm talking about, but is there any way that encoder could look at the inside of a cylinder instead of the outside of a cylinder? Because I see opportunities.
I don't know if Renishaw makes an encoder like that. They make linear ones, but I've never seen one that goes on the inside. Yeah, I was wishing for that, to be honest.
And Dan, how do you center the encoder ring? Is that done by tweaking the tripod support?
Well, that's a really good suggestion, or good question too, Richard. And I've done this actually several times. And as Marty's here, I noticed Marty here. I'm going to be doing it again. And I laid on the floor at North Carolina. It must have been 6 hours. And, it had a fairly slow slew speed. And I had to slew the telescope back and forth with a dial indicator and make an adjustment and hope I got it right. And I ended up getting it so it was well within the tolerance, but it took a long time. And this has an advantage, Richard, where all these are going to be CNC milled, all these holes, and they're going to be very centered compared to this. And so let's see if I can turn that back on. So as long as I follow this procedure, it should be fairly close right to begin with. And that, you know, nothing's perfect, and I'm going to have a way to adjust that. But that's a good question, and it might take some time.
It was a pain with the Cal Poly to center that, especially with the replacement ring.
Yes, I remember that.
Yeah.
Yes, yeah, it's always a challenge.
You could do 2 more little dovetail type devices. Since you already have the design, just make 2 more of them so you can move the thing back and forth in controllable small amounts and then lock it down.
That would be a real nice thing to do. I don't know, since they're not across from each other, it might be
But you could put them across from each other.
That was my first design.
Okay, 4 veins, and 2 of them are active and 2 of them are just loose sliders.
Yeah, my earlier design had 4 veins, so that's definitely a possibility and something I could think about. So I have 2 suggestions. That's nice. I love the suggestions.
Because you've already got the dovetail design and you know it works.
Yes.
And so you just make more of them when you're making them.
Well, we made 9 of them, so we have 9 of them now.
Okay.
Okay.
One more thought here. Could you spring load the read head so that if the encoder was a little bit out of round, the read head could just kind of travel along back and forth across the elliptical read head?
Yeah, you know what, a follower. I tried that on my 28-inch scope. I tried to get an encoder on the altitude, and I had a mechanism that tried to follow it because, you know, nothing was ever centered. It had like a roller bearing that followed the track, and I couldn't get it to work reliably. But it's definitely a thought, you know.
Okay.
See, we already have the dovetail, so if you had just a spring pressure and then you had a roller on there, that's an interesting idea. It might work in this case. So then there's 2 set screws, one that goes in there and one that goes in there. And in this case, we wouldn't use it. We would have to put a bearing over here and a bearing over here that would follow that. It's an interesting idea.
Well, Dan, my suggestion is to make this as finicky and as tricky to get it right as possible. So you're constantly flying down to Chile.
So I can get some views, yeah.
Yes. That's my idea.
Yeah, okay. All right, so we're going to move on to the telescope now. I don't have too much to show here. Those are my 2 major pushes so far. My next major push is going to be the altitude motor, and I threw some stuff up there that's just kind of, you know, they're going to be those are the right sizes because that's our standard motor that we can make. And that's an encoder. This is one of my worries, you know, one of my Dave Rowe gets paid to worry is this. Let's see. Okay, so this is the coils, and this has to be very, very stiff, and I'm going up all this way without any support. Well, I don't think that's going to work. I need to support this because magnetism and PWM that's not going to be, it'll be not good. So
can you define PWM for everyone?
Oh yeah, pulse width modulation. That's how most motor control systems work. They use PID, which is proportional integral derivative, and you position, you apply magnetism in exactly the right way so that it's always putting the torque to get the encoder to exactly where it's supposed to be at that particular time. And so that PWM just turns the transistors on and off for a varying amount of time. In an ideally balanced telescope with ideally low friction, they would be near 0 net energy. While, but then if the telescope is out of balance, it'll always be applying a torque one way or the other. And then, so these are everything below this surface, this yellow surface here, everything below that is steel. I like steel. It's easy to weld. It's really strong, and it's lighter than aluminum for a given stiffness. Sometimes that doesn't work out so well because it could be too thin, and aluminum can be thicker, so you can actually tap a hole in it. So, but that's kind of the philosophy. And I wouldn't call this a true Serrier truss because the poles are going to be they're going to be aluminum instead of steel. These are going to be steel down here, but it should help in some of the sag anyway. This is going to be fairly conventional at the top, the secondary cage. And these are going to be 2 1/4 inch pieces of aluminum. And I haven't designed the keepers for here and there. These rings look a little anemic. They'll probably be bigger, I don't know. And then I'll probably use some channels instead of this, especially by the eyepiece and the focuser. And I'll use a conventional spider, probably from, I forget the name of the company.
Astro Systems.
Thank you. And then I think he wants a feather touch focuser. Wasn't that it, Howard?
Yeah. And he'll want that focuser on the other side of the cage too.
You can put it on either side because all you got to do is
is
pivot it the other way, so you can just make it go over the other way. I spun this on this axis. I think I won't take the time because we're probably kind of late already.
We're a little late, but that's okay. We started a little late too.
Okay. I have a few more slides.
I have a question. I just have a general question about these direct drive motors. And you might not want to consider this for this job, but is there any reason why the altitude motor has to be a full circle? Because the scope is only going to go 0 to 90.
That's a good question. You're right. You only need a few magnets. You could do it with just a few and coils, although you'll be better off with torque if you use all of them. But that's an interesting thing. That gives me an idea, Rob. So what if I was to make a half a motor and make a double half a motor? So then I could have it all supported by this bottom part, and then I wouldn't have this up in the air stuff here.
Exactly. I'm thinking about the next super lightweight, smaller scope that really is portable, that maybe can make use of such motors if they didn't have to be a full circle.
Yeah. Yeah, we've thought about that in the past a lot, but I didn't think about it until this moment. So thank you for that. So I've already got several suggestions here. And that's one thing I'll look at, making a double partial motor to try to get rid of the bracing up at the top end. So that's an interesting idea. So anybody else comments before we move on?
I have a question that was typed in on the chat function from Akers, and he's wondering what is the pointing accuracy you expect before you make a point XP model and then after the model is built?
Okay, I think that's a good question, and I have a fair amount of experience with different kinds of things, and you can tell a good telescope mount right off the bat. You just turn off all the terms except for polar alignment, and you can just see, hey, this is a pretty darn good telescope mount, or the opposite of that. And I'm inclined to believe that this is going to be a pretty good telescope mount. So I'm going to guess that we'll achieve 30 arc seconds. We'll definitely be less than an arc minute without a model. That means that if you plop this down on the ground and you make it level, and you know it's level, and you enter the latitude and longitude, and you sync on one star and you don't have a model, you'll probably be able to go within an arc minute anywhere in the sky.
Dan, do you have 3 feet or 4 feet for the telescope over there?
Okay, good question, Tong. In fact, I was going to say that. I almost forgot to say that. So, whoops. Come on. What happened? All right. So these are the 4 feet, and they're going to be screwed feet, so they can go up and down. Now these discs, I initially drew them just as a disc, so you could reach down and adjust them to level it, right? Now here's my idea right now. It's instead of a disc that you reach down and turn, it's going to be a 3D printed timing pulley. And the timing pulley is going to have great, big, thick walls, long walls, so that the belt will never become disengaged. And then there will be a timing belt that goes around all 4.
Mm.
So if you loosen the timing, you can just use a drill motor with a timing pulley on the end, and you can like turn all 4 at once and raise it or lower it onto the wheels, the portable wheels, which I haven't drawn yet. And so to answer your question, Tong, there's 4.
Okay, so,
Yeah.
so how do you make sure it's all balanced? It's equally distributed.
Well, you just use your level, and
Okay.
you can feel the torque and
Okay.
yeah. I do this on my, I have 6 on my 28, and you know I spend a little time leveling it. Yeah, but
Okay.
yeah. Okay. Anyway, one of the things I wanted to say is this is kind of a unique telescope in a sense, because it is sort of bridging the gap between professional telescopes and amateur telescopes. So it's kind of a unique position, I feel. Okay. Any other questions before I move back to the?
Yeah, one more question on pointing. Does the temperature change impact the stability of the pointing?
Well, yes, for sure, but hopefully a very small amount. One of the things is the encoder's read head is mounted on steel, and it contracts and expands both ways, left and right. So that should not be a problem. Let's see. It will change the length of the tubes. I don't think that's going to be very consequential. So I don't know. I would guess not very much.
Yeah, I'd like to ask one little question. Since this is being used by a guy with a ladder who's sometimes up on the ladder, and from the Cal Poly, which we could slew at 60 degrees a second, I wonder if you could incorporate some bumper bars or something so that when this upper end of the tube collides with something like the ladder or the observer, it shuts off the power to the motors, or the motors are tuned in such a way that as soon as there's a significant over current, it de-energizes and doesn't push him off that 14-foot ladder.
Yeah, that's a good point. Well,
So, can I say something for a sec?
Yeah.
So in some of the microscopes I work on with that are SEMs, they have a collision detection system, and what they do is they put a small charge on the stage, and if the stage bumps into anything, it basically shorts that out. So if he's on an aluminum ladder and you've got steel trusses or metal trusses, you could put a digital signal between the two, and if it hits the ladder, everything shuts down.
Yeah, you know what? Those are really good points, and this is going to be a tall telescope. I think I have a eyepiece height here. We can take a look at that. And this eyepiece height, if you look down here, it's 145 inches. So let's do that in feet here. 145 divided by 12 equal,
12.1, 12 foot 1 inch.
yeah. Yeah, so that's, I wouldn't want to take a fall that high. You know what, another thing that I used to do a lot of quadcopter stuff, and one of the things we used was a sonic sensor. And we could use a sonic sensor and stop it before it even hits somebody.
Yeah, that's exactly what you want to do. You don't want to have a collision, or at least you don't want to have a collision with anything that's solid.
Yeah.
The Cal Poly, when you was slewing it at 60 degrees a second, you really would not want to have been looking into an eyepiece if you accidentally hit the wrong button. And instead of going away from you, it came towards you.
Yeah, yeah.
And it was a pushy beast. You know, it took a lot of force to make it stop.
Okay, I'm trying to write some of these things down. Let's summarize. So somebody had the idea about the encoder. Oh, that was Howard. Encoder ring mount. What was some of the other ideas? I thought I wouldn't forget them, and now I've already forgotten them.
Oh, the altitude direct drive motor not being the full circle.
Okay, partial altitude motor. Okay.
Having a dovetail so that the encoder could just follow the ellipse.
Then, since I'm just not quite convinced it's a direct drive motor is suitable for visual observing. You know, at this point, because the speed wise you really don't need the speed, right?
No, they would. I suspect he'll have it running pretty slowly.
Yes, it's
he won't run it at 60 degrees a second. I'm supposing he'll probably do.
Yeah. So what is wrong with the drive system Howard has been working on with? So can you compare with the two drive system? What's the advantage over Howard's drive system you can achieve for the visual observing?
Okay, well, Howard doesn't ever use go-to. Howard just pushes his telescope around, and he knows the sky by heart, or he uses a map. Am I right, Howard?
That's right. Yeah.
Yeah. So he uses the control system to track, and that's it.
But that's available. The go-to is available. It's just not using it, but it's readily available, right?
Yeah, but it's not nearly as accurate as this. It's by far. I mean, you know, struggling to do an offset sync on a nearby star, centering that star, syncing, and then moving over to the double star you want to take the images of. And then it drifts out of the field of view while you're doing it. Of course, that's not visual, but visual. The way that Jimmy observes is high power all the time, and he won't ever have to put a low power eyepiece in to find something. So that's going to be the main advantage of this.
I agree with that. Even for visual observing, I feel that, when you're looking at distant galaxy groups and so on and so forth, you want a pointing accuracy that's within maybe 10 arc minutes or 5 arc minutes. And at least currently his telescope has doesn't hit directly. He has to always go to a local star and do a sync. And I think that's the major advantage, right?
Yeah, that is. He'll be able to keep that 500 power or whatever power eyepiece is, and it will be 900 power, 1,000 power eyepiece, and it will be there, because we're going to be pointing. If he makes a 16-point model, my guess is he'll be under 10 arc seconds, because of point XP. He'll be able to point that thing within 10 arc seconds, and he uses go-to. He uses oh God, what's the name of that software he uses?
Megastar.
Megastar. And he finds the things he wants to look at, and he does a go-to to them. He's going to love this compared to the other one. I guarantee it.
Howard, have you ever tried use go-to function in eVscope?
Oh yeah, a few times.
Few times that it works. It works.
Oh yeah, Dan has helped me each time I've done it, and we've made a model, and it points wonderfully well.
So what's the accuracy you get from with your scope?
No, it's not 10 arc seconds, that's for sure. I would say it's about an arc minute.
Yeah, that's about what I get with my 28 before I'm doing these mods to make it direct drive. I'm getting about, I consider it lucky if I get an arc minute model.
Yeah.
Yeah, you guys are talking about some tiny numbers here. I have a 12.5-inch 10 Seggerty that is just sloppy. And, you know, I'm happy if I'm 5 arc minutes and typically more like 15 arc minutes for visual observing at low power. And that's the difference here at low power. It's fine. It works wonderfully.
Yeah.
But, you know, I'm at 100x, not 1,000. So,
yeah.
So if you the pointing accuracy is not that critical, right? So as long as it's tracking well, and what's the difference between the 1 arc minute and the a few arc second for visual observer?
It depends on how much magnification you're using.
Okay.
And because Jimmy's always using well above 500 power, you know, assuming it's a decent night. He's going to keep that 500 power eyepiece in the focuser if he doesn't have to search for his next target when he does his next go-to, which is pretty much what he has to do now on his 48-inch. And my prediction right now is that after Dan's finished building this 36-inch scope for Jimmy, and Jimmy's taking it down to Chile and he's used it, he's going to call Dan up again and say, hey, Dan, I want you to rebuild my 48-inch with direct drive motors.
Okay.
That's my prediction.
Okay, I see.
You know,
okay.
I might venture a slightly snide comment, since you can rotate the secondary to 2 different focus positions. Put an imager at the other one. Since the software for stack and track is now becoming mature, you know, after Jimmy's looked at this thing and squinted and tried really hard to see this 18.5 magnitude thing that he's looking for, he could spin the thing around and shoot 60 seconds perfectly tracked and go to 23rd magnitude.
I don't think you know Jimmy.
He might bump his head. Who knows? Yeah.
I know people like Jimmy. You know, sometimes they undergo a religious conversion when they suddenly discover 90% quantum efficiency sensors and what they can do in 60 seconds. You know, could happen.
You never know. Yeah.
Yeah. So, you know what? I think you misunderstood me. This doesn't have a rotating secondary for 2 points. You would have to put that in there. It could be part of the design, but what I meant is he could view it with either side of the, you know, I had it at 45 degrees. Let's say it was pointed to the west. You could also, without moving the azimuth, point it to the east. That's what I was talking about.
Okay.
So we're about a half hour behind our timeline right now, Dan. So
yeah. I'm going to go fast. Yeah.
Okay.
I'm going to rebuild my 28-inch with direct drives. And let's see here. I'm going to use I have a direct drive on the azimuth already. And I can use the existing mirror frame and mirror cell. I have to make a fork similar to Jimmy's. I'm going to do away with the strings and the folding secondary and add a rotator and focuser, which brings me to this slide. This is a bearing. I bought 2 of these from VXB, and they cost, if you look over here, they cost $17.30, $17.37. And they were remarkably, one of them was remarkably good quality. The other one was a little sloppy, so I don't know why there's different, but I started printing out, these are the scraps. Rob will appreciate this. These are the attempts at the, shoot, I can't think of the word. Anyway, then, you know, Taj is the expert at 3D printing, and he printed these for me. These are 3D printed timing belts. And so here's the more or less finished. So there's 1, 2, 3, 4 parts, and then there's one inside here that this black thing pushes against to put this roller on this Crayford design focuser. I designed it big enough so that a CWO camera will fit in one end. Whoops. That's my last slide, but I have one more short little video. This thing, I'm pretty excited about it. This is for my 28-inch telescope. And I started thinking about this, and for some dollars worth of PLA 3D printing filament and a couple of bearings and a couple of aluminum pieces. Let's see, I'll try to speed this up. Okay, so that's the timing gear, and it works really well, as you'll see in a moment. Look at that. Okay, it should start turning here real soon. Okay, it's a bad video, sorry. And it turns really fast, so if you have a direct drive telescope, it'll keep up with it to keep north up or whatever you want to do. And then the focuser works too. I'll fast forward. Okay, there's the focuser. All right, the focus is going to start moving here, so watch closely. There's the 3D printed timing belt. Okay, there it goes. And there it's moving in and out. So anyway, this is for my 28-inch telescope, and I'm pretty sure it's going to work just fine. And I do believe that that's the end of my presentation. I was going to say questions, but I think we're out of time.
Well, we've had a lot of questions along the way. So yeah, I think that's good. Well, excellent. That's exciting stuff. I can't wait until you get to the point where you're actually building this thing.
Yeah, well, I forgot to mention, we have all the motor parts for the azimuth motor ordered. They're going to be here in a couple weeks. So that's good. And then we'll start working. So I'm going to mute my mic.
Okay, very good, Dan. Thank you again. Okay, so next is Richard Berry. He's going to talk about the Unistellar eVscope, which I'm sure everyone here has heard about and probably has an opinion about as well. So Richard, you're up now. I see you've muted your microphone. There you go.
All right, I'm on. I will share the screen. There it is. And we'll go into slideshow mode. Come on, do it. Has it done it or not?
No, not yet.
No. Why not? Come on, you're being asked to. Oops.
That was closer, but we still see all your slides on the left-hand side.
I know. As I'm going to oh, I know what it is. You
Try clicking the little movie screen icon.
Okay, we got it. Okay.
Now you got it.
Yeah, it's always, the little bar on top kind of covers key parts of your menus.
Ah, yeah.
Okay. We've been talking about alt-azimuth telescopes for 13 years, and we've seen them happening in very, very big telescopes. And then this group, I guess about 3 years ago, began to wonder about an electronically assisted type telescope on a commercial basis. And I suppose that it was actually when they did the costing on it, they ended up with a 4.5-inch aperture. And they did one of these fundraising things, and lo and behold, they got a lot of interest. So early on, when the price was around $1,600 to buy in, I said, this is interesting. And then I waited a little bit and I bought in when the price was $1,900. So fine. I waited a year, followed their announcements, and the device came one day. 2 months later, we're out in the parking lot, lights all around us in Salem, and we are looking at the Horsehead Nebula from this kind of location near a large city. With a telescope where the guy who's observing there, he can look into the eyepiece or he can look at the screen. Either way, he's seeing the Horsehead Nebula. This is a game changer in many, many respects, because it means it brings easy to look through telescope to the general public for an amount of money that seems like a lot, until you begin to say, well, what's the alternative to actually have this kind of usability? And you can certainly do imaging with for a smaller amount of money, but you can't probably show the public things in the sky for that much money. So in January last year, it arrived and I ordered it with the backpack. So it arrives beautifully packaged and you get a tripod, a backpack, which is padded with about 1 inch of foam, and the telescope is inside. And then you get all the little accessories and stuff. So here this little guy is. It weighs 20 pounds. Okay, so when people see the pictures of it, they go like, oh, piece of plastic crap, you know, ain't gonna be worth a damn thing. It weighs 20 pounds. It is solid. I never took the coverings off because I wanted to keep them in good shape to be able to take good pictures of the mount. As at one point I was thinking, these guys need a good manual for this thing. I'm going to propose that I write a manual for it, and we'll sell a whole bunch of manuals and I'll get rich on that, right? Yeah, right. It's called making money by writing books. At any rate, it is solid. There is real metal in here. So even if it looks like it's plastic, it is not. I took it out. It was cloudy, of course, because the new telescope arrived. Pointed it at a signal tower on the opposite hill. And hey, look into the eyepiece. And yes, this thing works. First night it was clear. I kind of messed up. I had the forecast said it was going to get clear in the wee hours of the morning. So at 4 in the morning, I went out and it was clear, and I go inside and I grab the telescope, I set it up, and it starts to get bright. So here it is, a blue sky of morning, and I'm looking at Mizar. The telescope found Mizar all by itself. And this is what the eVscope does that the telescope you build yourself usually does not. This is a little bit later. I think this was back in February. I've set it up out in the pasture. In other words, I've set it up in the middle of the pasture. It's got a battery that runs it for about 2 nights, 2 observing nights. The lights on the device are dim enough that they don't disturb your night vision. The view, when you look through the eyepiece, is bright enough that even if you use a flashlight a little bit and you mess up your night vision a little bit, it's bright enough to see easily without good dark adaptation. And when I showed you that first picture in the parking lot, if we had been looking through an optical telescope with that much light around us, you wouldn't have seen anything when you looked into the eyepiece. The eyepiece is looking at an OLED screen, In other words, you're looking at a display device. It's bright enough that you can see what you want to see, but not so bright that it messes up your night vision. It's really a nice balance. So here's the eyepiece. It's just a rubber device. It's focusable, and you look into it. And this is my cell phone held up to the eyepiece, and this is a straight picture of what you see when you look into the eyepiece on that night. So let's look at the basic specs quickly. Aperture is 4.5 inches. Focal length is 450 millimeters. It's a motorized altazimuth. That's what this group was founded basically to talk about 13 years ago. So the sensor is a very nice Sony Exmor CMOS chip. It's not a particularly high resolution chip. As I said, 20 pounds. The footprint is 26 by 10 inches. So if you build a little box to carry it in instead of the backpack, it would be a very convenient suitcase sized thing. When you look into the screen, you're seeing an angular magnification of 50 times over what it looks like in the sky. It reaches visual magnitude of 16 in about 60 seconds. And this is not, this is something I measured. So it's not, that's what they claim, and they're correct. And you control it over a Wi-Fi link with your smartphone. So when you set it up, you turn on the smartphone, you link onto the telescope. The telescope can talk to 8 different smartphones at the same time. One of them owns the link. The others are passive watchers. So you can have a crowd of people around you all looking at the same thing, and one guy's driving it. For a star party type environment or a astronomy club kind of situation, it really works great. More specs. These are 3.75 micron pixels. There's 1.5 million of them. 6 millimeter diagonal, so it's really, really tiny sensor. If you look at the specs online, it's 10 or 12 bits. They're probably using 12 bits. It's a variable gain amplifier, and that is user settable. So the scale is 1.72 arc seconds per pixel, means it's a reasonable match to a 4.5 inch aperture, and your field of view is a little bit smaller than you'd really like, but actually, when you think about it, pretty good compromise. Focus. Well, people go, well, how do you focus this thing? There's a big knob on the back. Use pointer, and from being in very good focus to being slightly out is about 2 bumps. So it's a very easy to control thing. And when you turn this big thing on the back of the tube, it does not move the scope very much. It doesn't bounce around. The sensor is reading out, depending on how you have it set. It can do millisecond exposures, and the longest exposure you can do is 4 seconds. So if you're going to do something like focusing, we're using what they call live mode, and the exposure, I think the default exposure is 200 milliseconds. So it's bumping along. You're working basically live, real time. To focus, they have into the cover, into the cap, is a button-off mask. So you point it at a bright star, Rigel. You turn the knob until you're in perfect focus, and you're done. Once you learn how to do it, it takes about 15 seconds to get a nice focus. And so this is typically what the stars look like when it's well focused. They are not perfect little points because you're looking at a Bayer array camera, not particularly high resolution. Top to bottom is 1080 pixels in this circular frame. And the image, you can read it out two ways. You can get a circular readout and you can get a full frame readout. So here's Rigel. It automatically picks if you have it in auto mode, it will automatically pick a reasonably optimal way to display the image. I was very curious about what the dark frames would look like. So I shot and saved a whole bunch of dark frames, added them together, and then stretched the hell out of it. And here's what the dark frame looks like. Typical kind of thing from a CMOS. You've got some amplifier glow, and you've got hot pixels. And this kind of appearance is typical of Bayer array systems because single pixels are hot and they end up underneath individual or on top of individual pixels. When we initially got it, you would have brightly colored fake stars, which were kind of annoying because the initial software release did not have the capability of dark frames. There was a function in the cell phone that said, shoot a dark frame. You went to that and it said, sort of not let implemented. It will be soon. Well, they did implement it. And now if you shoot a picture, I shot this with and without a dark frame. The dark frame function actually works quite well. It actually shoots 5 dark frames in a row, 5 4-second exposures, and processes those to get a pretty decent dark. Mechanically, up close, this is what it looks like. This is the boss, which plugs into the heavy-duty tripod. There is a metal structure in here. You can see there's a brace. There's probably a steel frame, and it's geared. So when it runs, you hear, a little motor driving a gear. It doesn't move very fast, something on the order of 2 degrees a second. So it takes a while to get places. Looking at the bottom, you have a power goes in here on a USB 3, and this plugs into the tripod. Here's the tripod. The tripod is not just an ordinary camera tripod. It is very solid, very nicely machined. It can extend up to about 48 inches high or down to about 26 inches high, something like that. Looking in the front, you have a support structure. I wondered for a while why they use such thick supports and why they sculptured them this way. If you think about what the diffraction pattern this will produce is, it's going to have nice aesthetic spikes on the stars. But because they're wide, there'll be short spikes. And these curved veins here will give you kind of a slightly soft-ish star image. That's the way people think, the general public thinks of the way a telescope should look. The inside is shiny, but not excessively so. You can see the mirror at the bottom. This is an angled view looking at the sensor, which is located inside. And then, of course, if you look into the telescope, you see the sensor imaged out to infinity. And here it is, all 6 millimeters of it. There's a window in front of it. People say, well, I bet you they don't use IR rejection filter from the color of this and also the images you get. I'm sure they do use an IR rejection filter. And I'm just going to go back. People say, well, you can't put a filter on it. Well, you can. You'd have to make a special little thing so that you could reach in there and put it on. But if you wanted to put a filter in, like a light pollution filter, you could. Basically, they take care of that with very good image processing software. It is very, very good at rejecting the high background levels. So here we look into the eyepiece. It's this rubber thing. And you get a view like this. This picture was actually taken from that lighted parking lot scenario. This is a longer exposure. This is a cell phone photograph into the eyepiece. And the cell phone exposures are typically, at least with mine, 1/10 of a second or so. So you can handhold it quite easily. So let me give you a little bit of a rundown on how the thing works. Okay, you put the tripod down, you level it. It's got a little bubble level to make that easy. You turn on your cell phone and Wi-Fi link to it. It took me a while to figure out how to do that with my smartphone. That was the slowest part of it. You have to go into those settings menus and mess around. Okay, so you set the thing up, you put it on, you turn it on. The range of the Wi-Fi, by the way, is about 100 feet, which means that you can walk around and talk while other people are looking in. So if you think of a public Star Night kind of event, you can be off gesturing and waving your arms while other people are taking turns looking at their cell phones and looking through the eyepiece. Okay, so we've just turned it on. The software allows you to select a target. You select the target. Okay, this is your first observation of the night. And then the device does the following things. First of all, it slews away from pointing straight up, because when it's stored, it's pointing straight up. It slews down about 30 degrees. It shoots the first exposure. These are, I think, 200 millisecond exposures. It then moves 90 degrees in azimuth, shoots a second exposure. That's enough to get since it knows it's been where it's pointed, and it knows how it has moved, that's enough to get a plate solution, a rough plate solution to give you the whole sky, not an accurate one. So then it moves somewhere near the target. It's usually within 5 or 10 degrees of the target, shoots a third exposure. Now they can get a good plate solution. It now moves to the target, usually within maybe the central quarter of the field. Shoots a target exposure, refines its pointing, and then this whole cycle has taken about 60 seconds. And now you're tracking the target in live mode. So it's figured out what it has to do. It's driving both motors at the same time, and it's following. Okay, now you can, at this point, play around with the settings. You can push the exposure up to 4 seconds to go a little deeper and stuff like that. But if you use the little digital joystick, you can move things around in the field. So you can compose the picture nicely. You can put the right part of the Orion Nebula where you want it to be, et cetera, et cetera, et cetera. Then you can pick something called enhanced vision. And this is when it begins to shoot exposures and stack them. And the image gets better as more and more frames are stacked. They're stacked in real time, and it's taking care of both tracking and rotation at the same time. So this is a quick view of what your cell phones, these are screen grabs from the cell phone. So you can be looking at, this is the whole frame of the image. And if you turn it on its side, you now get a modified version. This is the joystick. This is the turn on enhanced vision. This is the find your way. And this is the function that gives you information about the object. The Orion Nebula is X thousand light years away and blah, 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 and blah, blah, blah. Okay, the other items here, you've got the startup screen. You've got a find me things. This is the science applications. This is the extra functions, and this is, oh geez, I forgot. Oh, this is a function allows you to send your data in when you're doing science stuff. Those same functions appear, and you get a nice big, larger screen. And they have apparently just in the latest software release, you can now, the way I would have to do it, and all the pictures you see that are full screen that I will show, you had to use the cell phone's screen grab mode. Now you can save it directly from their software to get the full sensor. So you've got a nice little telescope, you set it down, and you go for things like the Orion Nebula. It's, you know, this is the way the public wants to view things typically. Objects like the moon, you can vary the exposure from just looking at the crescent. No problem, it's made for deep sky work. So bingo, you can get the Earthshine on the moon. This is 2 minutes worth of stacking. And it likes things that have a lot of red in them. You can see this is relatively early. This is in February still. And I've still got the hot pixels in these frames. And then you just go on a tour of, you know, all your standard objects to see, well, how well does this thing work? If I'm out showing my friends who are not so much astronomers, I get the Whirlpool Galaxy in, and then when you've reached, after it's been looking for 3 minutes, and people are looking in it, you know, right away. By the time you get to 3 minutes, you have something that is not too shabby, especially if you're considering that you're not in a particularly good site. So here's M101, which is dim, or at least low surface brightness. And it's a 4.5-inch telescope. You get big surprises when you say, well, gee, I'll you know, look, well, here's some, which guy is this? This is one of the variable nebulas.
Hubble's variable nebula.
Hubble's variable nebula. This is also a very interesting frame because if you look at this closely, you can see its tracking. Those are the hot pixels that it has not resolved. Okay, so you guys are looking at this on a computer screen, so you can see them quite well. So that's its native tracking. It's stacking a bunch of images like that. So you're seeing the tracking and then the software stacking working together. Crab Nebula looking pretty decent. If you think back to what the Crab Nebula looked like in your first 4-inch telescope, this is better than that. You can just plain have fun. You can go through the back end of Leo, looking at one galaxy after another with 2-minute exposures. And here's the third member of the Leo trio. M81 and M82. Again, 5 minutes, because to get the outer spirals, you really needed a longer exposure. M82 is pretty high surface brightness, so it's real easy. The Owl Nebula looks decent. This is when it really hits you. I'm looking at this stuff in color. Okay, that's kind of sexy, because, you know, I could discern the faintest pinky tones, I think, in the Orion Nebula with my 20-inch scope. In the Orion Nebula, I'm not sure I ever saw color in any other sky object that would be considered a deep sky object. This is, I tested it. I shot a lot of pictures of fields that I happen to have magnitude sequences for. So this is V405 Aurigae. Here it is. I did astrometry on it and find that you can get position of an object in this field to about 1 arc second. So it allows you to do, you know, science without using their science functions. And for the heck of it, you may remember that the New Horizons spacecraft, when it got 40 AUs out, it took a picture of the star Wolf 359. And this is my picture of Wolf 59. In the picture that New Horizons taken, the star is shifted slightly from parallax. So my assessment is, if you have friends who want to be able to see this guy, and you're going to be in any public event, probably in a place that the public considers reasonably safe, meaning too well lit for doing good astronomy, here you are. And then, you know, you play around with this thing and you keep going like, would I have spent the time to actually go and look at this cluster if it wasn't so easy and so much fun to do it? So here's an Asian Chi Persei. Objects like M31 are actually too big. So anybody who's looked at M31 in a large telescope has got this thing. Yeah, the object completely fills the field. You can see dust lane. Same thing here. It's a relatively small field of view. Does nicely on objects that are visually usually not very impressive, like Triangulum. And here, by the way, this really shows off nicely. I'm sure the designers sat there and they said, well, how can we get nice little crosses on the stars? We'll put this funny diffraction. We'll use the spider that supports the imager to make diffraction spikes. And they've been very successful from an aesthetic standpoint. M67, I took this because I wanted to do magnitude sequences and find out what it could get down to. And like I said, 60 seconds, 80 seconds, you're down to 16th magnitude easily. In probably about 20 minutes, you could get down to about 18th, maybe 17 and a half, something like that, in a good dark sky on a cold night. And then if you work at it, you can get rather pretty pictures. So that's all, folks. I'll take questions from here.
Okay, we have a question from the chat function, basically asking, does the experience of looking at the sensor give you the sensation that you're actually observing compared to a telescope where you're actually using an eyepiece where you're getting the photons themselves?
It does and it doesn't. The image is very slightly soft, but, and it's because I've been observing for years and years, so I look at it and say, it's too bright to be real. On the other hand, if you're relatively naive, you're going to look into that and say, oh, I'm looking into a telescope and I'm seeing a real object in color. And it looks like I imagined it. One thing you may have noticed in the pictures, they do not, their default software settings do not hype the images up. Okay, they're relatively soft. They're pretty realistic. And yet, because they're brighter and in color, you know, you can see a lot more. You can see what you always wanted to see. And that's when you realize, you know, that's what M51 looks like in my 20-inch telescope from a pretty good sight. And I'm looking through a 4-inch telescope. So there are people who are going to hate it. There's no doubt about that. And there's people who are going to go like me, who go like, yeah, I'm 74. My eyes aren't quite so hot. And this, you know, this works great despite, you know, a certain amount of haziness in my vision. And I wouldn't be able to see these things this well, you know, with a 4-inch telescope that did not have this enhancement. My general sense is that if you can see your way through to spending $3,000 to really scratch an itch or to do public events, or you're willing to go in with like 4 or 5 or 10 other people and say, we'll share this thing and we'll use it for our own private star parties and we'll take it to public events. Well, that's $300 a piece. Okay, well, you can't buy an eyepiece for that much, hardly. And this thing is the whole telescope. And you put it down, and we've all been through that experience doing public stargazing, where you're trying to find something you've found 1,000 times before, and you can't find it. And so there you are with your neck hurting, trying to find M51, which is straight overhead, and you can't get the damn thing into the eyepiece. And you know I should be able to find it. This thing lets you, when you're dealing with the public, this product lets you focus on the people you're talking to, instead of putting all of your effort into making the telescope do its thing. And so to some extent, it's a moot question as to whether it looks like looking through an eyepiece. It's delivering the goods in key respects.
So, Richard, I know this discussion has been had on the Oregon Scopeworks email list, but for those who weren't part of that, what do you say to the people who comment that, yeah, that's all well and good to have a telescope at $3,000 that can do those things, but I could get this camera and this sensor and all this other things and make my own, and come up with something even better. Well, what do you say to that?
Do it. I don't have any problem with that. But I'll challenge you to take that setup out and set it up in a public park and have the people who come to look through your telescope go away happy. Because you're going to be going like, well, I'm clicking here and I'm clicking there. And you're not paying attention to the people you're trying to show things to. And when when I'm imaging with the Roe Ackerman scope, which is out in my observatory, and I'm sitting in my office indoors, I have a very different attitude toward observing. This is doing a job. I'm shooting pictures. I've foregone the joy of looking through the eyepiece. And instead, I am looking at this variable star going through its cycle, and I'm shooting a picture every 10 seconds for the next 6 hours. And that's that's my kind of astronomy. And when I do a public night, I like to be able to talk to the people instead of messing around with the equipment. And I still like looking through telescopes, but as I've gotten older, somewhere around when you pass about 50, your eyes do something like the pupils don't expand all the way anymore. And you're suddenly always stopped down to 4 millimeters pupil or iris, Visual observing is really great when you're under 30.
So Richard, I've got a question as far as public outreach goes. Could you send the signal to like a video projector and project it on a large screen for an audience that needs to stay 6 feet apart?
Yeah, or they could look at it on their individual cell phones, standing as far as 75 feet away from the telescope.
Right.
No, they will. I've talked quite a bit to their principals, because I mean I was trying to talk them into letting me write a book about this thing. And I said, give me enough technical information and I will write you the best book anyone's ever written about this telescope. And they were, well, we haven't finished the software yet. And it's like, lead time, guys. It takes me 6 months to write a book. By the time we'll finish, we'll tweak, but they're not writers and they speak French too. So I've sort of lost the question, but
yeah, I was just wondering, if you've got a reasonably large group of people, rather than having them all looking at their individual phones, if you could project it on a big screen, it feels more like a public event that way.
Yeah, and they have promised that they will have software for PCs. Okay, they started out with cell phones. You can now install it on an Android tablet, and it worked great on my Nexus 7. It was really nice. And they will have software for PCs. And when they have software for PCs, you can do anything you want with it. I mean, you can broadcast it over.
Well, actually, if it'll do an Android tablet, you can already mirror your image onto a projector screen. Yeah, that'd be easy.
Yeah.
You could Chromecast it, or you could use AirPlay as well if you've got an Apple device. So I think once you get it on one handheld or one device, then you'll be able to broadcast it to others.
Yeah. The limitation with cell phones may be that it's occupying a Wi-Fi channel talking to the telescope. You may not be able to get the signal out any other way. And but I mean, once you have a you know, I mean, this is there. I think they just haven't gotten it together yet to do the PC version. Once they have a computer version, you know, I mean, they know that it will be reverse engineered like about 10 minutes after it appears. And this device is, the cell phone is not doing the computation. A lot of that computation is occurring in the device, which means that it has to have a fairly simple command set, right? And it's returning, oh yeah, when you hook onto this thing, it's a 75 megabits per second. So you got a good solid information channel with your telescope. When you go into the into one of their science modes, I didn't talk about this, but the SETI Institute is working with the Unistellar people on programs for doing things like photometry of Earth crossers and stuff like that. The SETI Institute is one of their big selling points is we're going to be hit by an asteroid. So they're doing occultation, asteroid occultation stuff. In the science mode, you can set it to go to this RAN deck, shoot this many pictures at this exposure, and save them in memory. Then the next day, you upload that to the SETI Institute. They combine it with data from 50 other people who observed with their Unistellar eVscopes, and they make a measurement of the asteroid shape because of who it crossed over and so forth. And you've got accurate timing for doing this because you're sitting on a cell phone, which is tied into the time basis. The other thing I will say to people who are going like, well, I could build the same thing. It's like, well, you've had the last decade and you haven't done it yet. So, you know, if it's all that easy, you know, what's your time worth?
I think there's one other company that's a competitor, and I think they're called Vaonis or something like that. And
yes, they are. Their system is more of a photography unit rather than a visual viewing kind of thing. So they're taking 6 megapixel images with an 80 millimeter f5 refractor. And they have just introduced a device similar to this with a 50 millimeter aperture system with a 200 millimeter focal length. So that would be a quarter as much light as this. They're selling it for, I think, 1,050, something like that. That's the crowdfunder price. It'll probably be about twice that, I guess, when they go public. But this technology is scalable. It's all software. Is the magic.
Yeah.
And no reason you can't put an 8-inch mirror or a 10-inch mirror or a 12-inch mirror in, and the same software and just bigger gears and stuff like that will do the same stuff.
So I wanted to object, and I was on mute, but when you said, you know, why haven't we done this yet? And honestly, we have, not to the level that these guys have in making it slick and professional and really user friendly, but in the spirit of a rising tide floats all boats. You know, I'm sitting here thinking about what you've told me, and I start to feel a little bit threatened, and then I'm like, wait a minute, no, this group here is gonna grab onto this idea. Maybe there's too many naysayers right now, but this group is gonna grab onto this idea, and we've been putting this technology together and doing it in our own way. and you talk about this Unistellar talks about the science that they're able to provide. I think this is going to be a big game changer, and we're gonna end up doing things differently because of it. And it's just going to be good for everybody, you know. And there's still going to be a place for visual observing. There always will be. But
oh yeah, I mean, the ideal thing to do. This thing is not good for the moon and planets. Okay, the 50x and 2 arcseconds resolution, effectively. Yeah, I mean, what you want to do is you want to set this thing down beside your C8, which is looking at Jupiter and Saturn and the moon and Mars, and you're showing them the galaxies with a little scope they look into, and they're showing them the planets and stuff like that at 150x with an 8-inch aperture. And then if you take that C8 and you point it at M51, they're going to look in and you're going to get you've heard that reaction. Do you see it? I think I do. Is it the little fuzzy blob? Did you see 2 fuzzy blobs? No, I only see 1. You've been there, you know it. This thing, they look in it, it's like, oh, wow. It looks like a Hubble picture. And you go, well, not really, but no, I think this is, I think, what Meade and Celestron and every other manufacturer wish they could have had. And their problem in developing that, they had the telescope, they had the telescope platform, but they looked at it and they probably said, well, gee, we'll destroy our core business. And I don't think they would have. They wanted to keep the telescopes. They did not want to automate the telescope as fully as it has to be automated to do this.
That's another
yeah,
thing that
they missed the mark. I think it just makes it better. If we took a Unistellar apart and put it back onto a C8 or a C14 or something like that, it would just be it would be incredible. It'd just blow it away. But anyway.
And put a better sensor on and probably more horsepower. Like, do you know what the CPU is inside of it, Richard? Like, is it a Pi or something, or is it just something homebrew?
I don't. I mean, realistically, they had to have something that they could get commercially. I mean, they had about a 3-year development cycle. I could not get much technical information out of them. So the answer is, I wish I knew. And I never wanted to take the covers off of mine, because, you know, when you take off those nice covers, you never get them back on quite right. And your scope always looked like a little bit cockeyed and stuff like that. It did survive being dropped a couple times, so it's pretty tough. The worst accident I had with it is I tripped on the charging wire and yanked it out of the socket, and the socket survived, but you had to put it in and kind of wiggle it a little bit before the charging light would come on.
And what's the there were 2 ports on the bottom, right? There was a USB and then a micro USB for the power. So what was the regular USB for?
Undetermined. I mean, I'm sure that's what we really want to know. That's probably how they program it or something. But you know, I wish I knew.
I guess that also to add features later. Like, let's say tomorrow they decide that they want to add some other thing. They can just use the USB port to provide that functionality to people who already have the old hardware.
Mm-hmm. Yeah, I mean, as I said, I never took the covers off. I wish I had, because you know, in retrospect, it got burned up in the wildfire, so it's gone. And I could have messed it up as much as I wanted and taken it completely apart, and I'd still be right where I am now with it. I'm fairly seriously tempted to get another one. It is on sale right now for 10% off. So, you know, if you want to put together a little consortium of 5 other guys to play with one of these things, that brings the price down to a level where, you know, an eyepiece, a good eyepiece. 10 people is down to a medium eyepiece. A small club that wants to do public outreach, it's a no-brainer. You know, if you're serious about doing public outreach, this thing sitting with 3 or 4 other visual scopes, a couple of Dobbs and a C8 or 2, you've got a nice comprehensive thing where you can show them double stars and galaxies and the moon and planets. And yeah, you can broadcast it onto the screen too.
The Eugene Astronomy Club, we're seriously talking about getting one of these about the time the COVID restrictions are loosened up a little bit. We're thinking this would be a really good way to inaugurate a new generation of star parties.
Yeah, and I mean, you saw my first picture there. This informal thing. I think it was in the February, right after the February meeting of Night Sky 45. It was clear, so we carried the thing out, set it down, turned it on, and a minute and a half later, we're looking at you know, galaxies. Actually, we were looking at, I think, the Flame Nebula, probably. We started with that, and then we went to Orion. And then somebody said, well, can you see the comet with it? I don't remember what comet that was in February 29. Yeah, in February. But James looked it up on his computer. We plugged in the coordinates. And there it was off on the edge of the field, because we didn't, you know, the comet was moving fast enough that from 0 UT to whenever it was, it had moved a little. And that's, I think, when we just looked up the coordinates online and plugged them in. That's when people were kind of like, holy cow.
One other question, come to think of it, is this wholly self-contained, or do you need an internet connection in order to run it?
No internet. It's a Wi-Fi. It becomes a Wi-Fi, whatever you call it.
But
So
if
you
your
log
cell phone, if your cell phone doesn't have service, you don't have to. You can still run it.
Yeah.
Okay. Cool.
I mean, my Nexus 7 did not have a cell phone kind of thing. It's simply the biggest, strongest Wi-Fi connection around. And it shows up as a six-digit alphanumeric, and you just join that thing, and all of a sudden you're talking to the scope.
So I have a question, Richard. So I wonder how you and Eleanor are doing after all this stuff. Could you comment on the, you know, how you're doing after the fire and losing your house? And,
Well, I'm sitting in a warm room. Eleanor's cooking dinner. We are so we have all the basics of life. We have a bathroom, a kitchen, a little dining table, a little workroom that I'm in, and a bedroom. It's a, you know, a small, it's just what they used to call a mother-in-law suite in one of Eleanor's friends' basements. We're now when you get out of a place and you take nothing with you, you don't have anything, and that's when you begin to realize, gee, we should have taken underwear. The problem is, you know, we've been isolated in COVID totally for 6 months practically. You know, all of a sudden we're attending super spreader events at Costco to buy clothes. And when we got out, first of all, the cell phone went off at 2:30 in the morning. It's going, eh, 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 eh. I pick it up and I look at it. It's I couldn't see a damn thing. My eyes were totally bleary. And Eleanor says, we better find out what it said. So she looks at it and says, leave now, level 3, get out. So she packed a bag. She packed 2 bags, she says. I threw my computer with no peripherals into the car, a bunch of hard drives, and a box of my old photographic negatives going back to 1962, right? I then went out on the driveway there's a 40, 50 mile an hour wind, really hot, blowing through here. There's blowing limbs out of the trees. Okay, so there's all this big stuff that's come down on the driveway. So I cleared those out of the way, and I mean, the air was like totally unbreathable, and I'm breathing it. I mean, so I knew that for the next 3 or 4 days. And at just about 3:30, all the fire trucks in the universe pull up from the east on Highway 22, and they all line up, and there's people going back and forth and talking, and then they all pull out. That's apparently when the fire department's got the get out of there before you get trapped message. And so they all went east somewhere. They went west, I'm sorry, yes. Yeah, the same way Eleanor's talking, they went the same way we did. So visibility was about 75 yards, and it was smoky. So we drove to the state fairgrounds, which we're supposed to go. And had about, lots of smoke going over. We kind of go like, we sure hope it doesn't burn down our house. And at 9 o'clock, the Red Cross people come around and say, well, gee, we're not set up for feeding a lot of people yet. So why don't you guys go off and get breakfast? And you've already filled out the contact forms. And the Red Cross, basically their job was, they were going to find hotel rooms or something for, about 1,000 people, which turned out not to be an easy job. And, but we drove over to Denny's, and Eleanor's friend called and said, I have the mother-in-law suite in my house. Would you like to stay with there, for the duration? And yeah, we thought that might be 2 or 3 days. And it wasn't. So we got our next door neighbors snuck in. The police had not yet gotten the barriers really set up people proof, and they went on our back roads, and they got a message saying, we hate to tell you this, but your house burned down. So did your barn, so did your shop building. It's all gone. And our shop building burned down too, but our house didn't. And boy, are we glad that the propane tank didn't blow up. So it's, so right now we are doing things like putting straw on the slopes to prevent erosion, because the fire burned all the organics out of the soil. And now we have a slope on the south side of the house that goes down to a lower level. And that soil is going to erode when it starts to rain on it. So we were spreading straw about 2 inches deep on the top of the slope last weekend. So that's the story. So we're probably not going to go back and build on that same site because Highway 22, since we moved there, Highway 22 has gotten really noisy, very busy. And, you know, it's quiet after about midnight. The rest of the time it's just traffic going by. And we're also getting a bit on the old side for taking care of 8.5 acres of land. So, and the insurance company came through very well. So
Good.
we have money to buy clothes.
So what's the thought then? Are you thinking of relocating to another site entirely or building on a different part of the property or what's the plan?
Well, if you build on it, we're thinking of looking for another house, basically. We had a big house and the family that had built it had 4 kids. Okay. And there was 2 of us and my big workroom and my nice shop full of telescopes. And we were looking to downsize. And the big problem with, you guys are maybe a little few years shy of going like, we need a smaller house. When you do this and you've had many years to accumulate and build and do neat projects and stuff, you got a lot of stuff and you don't know what the hell to do with it all. That's a lot of decisions. And we didn't have to make any decisions. It's just all go on. So, you know, it's kind of like, well, what do you do now? Well, we start over, you know. The feeling is like you went on a vacation and you're out there having a good time at some resort and you get a phone call that says your house is gone. Well, so what do? You don't have to go home. You could go anywhere. Sort of, there's a certain amount of freedom to do this. You know, and you relieve the burden of figuring out what to do with it all. That sounds funny, but it's true.
I get it. I totally get it.
Yeah, if you've been through downsizing, you know about it. If you've done a late in life downsizing, you know all about it.
Well, it sounds like it's a do it a little at a time on a regular basis and stay on top of it. Yeah.
Yeah. Good luck.
Yeah.
Yeah, right. It never works.
It doesn't happen. No.
So we were evacuated too, probably maybe a little bit after you were evacuated, and we were gone for several days, and then we came back, and you know, thank goodness everything was as we left it. So.
Yeah, excepting it probably all smelled like smoke. But
oh yeah,
yeah.
Yeah.
I mean, but that's trivial. You wouldn't mind that. Eleanor is making noises like supper is ready.
So. I think we've probably gone long enough for tonight anyway. I think a number of us are probably hungry. So why don't I just wrap up by saying thank you to you, Richard and Dan, for your presentations tonight. And that tomorrow we start at 5 p.m. Pacific time, and we'll have 4 presentations. Rob Brown will talk about spray silvering update. Ed Allen will talk about his forced ventilation system, which I've just installed on my 28-inch scope. And then Mel will talk about an update of his 30-inch slut meniscus mirrors, which he's in the final figuring stages of a matched pair. And then Rob will close out the evening with the talk about his new spectroscope, a visual spectroscope, and I'll have a few words to add to that as well. So again, we'll start tomorrow at 5 p.m. Pacific time. And thank you all very much for joining in and making our first evening go as well as it has. I'm really happy with how everything has turned out so far. So.
And thank you, Howard, for all.
Thank you, thank you, Howard.
Thank you, Howard.
Thank you,
Oh,
Dan.
yeah.
Thank you.
It's been
Thank
my
you,
pleasure.
everybody.
And
Good night.
a lot of that
Richard,
thank you
thank
goes
you.
to Akers, who has been a major factor in getting me up to speed on hosting a Zoom meeting.
You did very well.
That's been a huge help. All right, so
At least we don't have to wear masks.
well, no masks.
That's
right.
true, right?
Yeah.
But one
Good
thing
night.
we'll end on.
Thank you. Thank you,
Make sure you
everybody.
wear pants. That's all I got to say.
Yeah.
Okay.
All right. Good night, everybody.
night.
Good night.
Good night.
Good
Bye,
night.
everybody.